So today I want to go over this paper here, MetaICL. I think this is a pretty influential paper when it comes to the training of large language models, especially in kind of a paradigm shift from pre-trained models into the post-training era. And yeah, let's just jump straight into it. Before I start going over the paper, let me give you some context. So this paper is called MetaICL. It's published by Meta and researchers at the University of Washington. And it was published in 2022 with, I believe, a preprint in 2021. So it's quite recent, but it also kind of highlights how many advancements we've had over the past 4 years as of 2025. So before I hop into the paper, I want to kind of give you a brief outline of how large language models are trained and deployed in 2025. So I have a comparison to 2021 or 2022, and I'll also go over how this paper introduces kind of new techniques or new concepts in machine learning. So you might have seen this before, but currently in 2025 and beyond, although really this there's kind of a question mark, especially because of how fast machine learning is moving. Large language model training goes pretty much this way, where you start with a model architecture, and you have a large data set, and I mean really, really large. And on this large data set, you pre-train the model first. So this pre-training phase, it is training the model itself, but really why we consider this pre-training is because all we want the model to do here is kind of gather knowledge. So maybe in this data set, and usually these data sets are massive, they contain a large portion of the entire internet. The goal is to have the model gather knowledge. So common proper nouns, common phrases, common words are kind of built into the model as weights in some way. So this is the first point, and the second point is to build semantic understanding, or language understanding in some sense. So what I mean by this is, after seeing a bunch of text of, for instance, English paragraphs, it's able to understand the general structure of an English paragraph. It's not able to reason about this. It's not able to understand what exactly the paragraph means necessarily, but it understands what a paragraph looks like. So the entire goal of pre-training is knowledge and language understanding. So the main goal here is language understanding, or language structure understanding. It might not necessarily understand the language or reasoning in the language as much. It also might not be able to respond to actions. So at this point, if you pass an input to the model, for instance, you ask it, what is the capital of Canada, then it's just a completion model at this point. So because the large data set here isn't really labeled, it's just a lot of language. So it just knows how to complete this, kind of like an autocomplete. So if you ask it what is the capital of Canada, it might continue just asking more questions about Canada. So it's not question answering at this point. So it's not QA, and it's not fine-tuned. So it has a very broad understanding of kind of everything, but not a very fine-grained understanding of anything. So after pre-training, you go into kind of instruction fine-tuning. So IFT stands for instruction fine-tuning. And in this phase, you have a large labeled data set. So this can be done in a bunch of techniques. So you can just do, a fine-tuning like SFT. You can also do ROHF. So there's a bunch of ways of doing this, but the idea behind instruction tuning is you have this pre-trained model that's able to understand language structure, but you want it to be able to respond to questions instead of just kind of completing existing sentences. So at this point here is where you have a labeled data set, and this is typically significantly smaller than your pre-trained data set. And these are kind of question answer pairs. So here your data might look something like, what is the capital of Canada? And then you'd have a bunch of responses to this question that you train the model on. So maybe you have, response 1 that says, oh, the capital is ... Or you might have response 2, which says, that's a great question. And then, says the capital, or you get the idea here. So this is the idea behind IFT. I don't have much space here. Let me make all of this a bit smaller. After IFT, you kind of go into the reasoning phase, and this is significantly newer, I would say. So reasoning kind of came as a consequence of realizing that chain of thought and reinforcement learning works well. So there's kind of two ways you can do chain of thought. So there's something called chain of thought in reasoning, where you train the model. So this here is where you train using reinforcement learning to think. So the model kind of learns implicitly to think before it responds. Versus you have reasoning that can just be kind of forced out of the model after IFT, just by encouraging the model, maybe using the prompt that you pass into the model to spell out a reasoning. So this is a forced method of doing chain of thought that does not need necessarily too much reinforcement learning. But this reasoning chain of thought typically uses reinforcement learning. So for instance here, DeepSeek R1 was one such agent, and I think DeepSeek was one of the first large-scale open source models that showed how they employ reasoning, and they use GRPO. And for instance, they might train on mathematics. So if they want to train on a bunch of integration problems, they might have a set of reward signals for each of the model responses. So suppose you pass in this problem as an integration problem, just x dx, and we know that the response should be x squared divided by 2 plus c. We have this sample labeled in our data set. So this is the question. This is the solution. And when the model produces a solution, we might have a set of reward signals. So your reward signals might look something along the lines of, is the expression literally correct? So, is your answer literally x squared divided by 2 plus c, which is what we labeled as our solution here? Or is it mathematically equivalent? Is it numerically correct? So numerically equivalent. Or was the reasoning process behind this long? So the length of reasoning could play a factor here. Maybe we want longer reasoning. Maybe we want shorter reasoning. Is the format of the expression correct? Maybe we want the expression to be output in LaTeX, or we want it in a different format. So is the format of this expression the way we expect it? So all of these are reward signals that we can use. And what we would do here is we would look at this output, and let me get a pointer. We would look at this output here, and we would evaluate, or we would look at the model's output for this question, and we would evaluate the model's output based on all of these reward signals against our ground truth solution. So this is typically what's done. After this, you can do further fine-tuning, either after reasoning or before reasoning without any reasoning. So after this, you can just fine-tune. So this is just regular supervised fine-tuning to specialize on domain knowledge. Reasoning also does this. It also specializes on domain knowledge, but you can also just do supervised fine-tuning for that. So this is kind of an overview of what the training process, very high-level overview of what the training process for these models looks like at the moment. But when this paper was written back in 2021, and I guess the researchers probably worked on it throughout 2020 as well, we didn't really have all of this. I mean, we had GPT-2 come out around that time, and the research paper goes quite into detail on experiments with GPT-2. But that's kind of all we had. Near the end of this paper's kind of lifespan of almost being fully published, that's when GPT-3 came out, and GPT-3 was what introduced these notions of for instance, in IFT here. So in 2021, it looked very, very different. And I can just copy and paste this here. I can copy and paste this part, and that's pretty much all we had. This is pretty much all we had. After which we had the fine-tuning phase, because I guess we understood that having specific domain knowledge would be good. In fact, we had the fine-tuning phase for a very particular reason, and that reason was, well, two reasons. The first reason is this data set is messy. So there's a lot of noise that we might not want the model to learn. So this is bad for the model to learn. And we also kind of had this idea that machine learning models are made to do specific tasks. So in today's world with modern language models, they're able to perform a wide variety of tasks. They can do things like classification, they can do sentiment analysis, they can do generation, just text generation or image generation. They can do question answering. they can extract knowledge. So knowledge extraction. They can do a lot of things, right? There's a lot of things they can do. At the time, the idea was that, well, pre-GPT-2, the idea was we would kind of need a particular model to do a particular thing. So you would have a QA model, you would have a knowledge extraction model, you would have an text generation versus image generation versus sentiment analysis model. So all of these were separated into different models because we didn't have the notion of, this model is powerful enough to do everything. So fine-tuning was pretty important back then, also because we want to specialize. So this hypothetically should end up cleaning noise learned, as well as specialize on a task or on some domain. We don't really have a task yet because we don't really have instruction and tuning yet. But with GPT-2, even though this is kind of all we had, the model was still somewhat able to respond to questions and was still somewhat able to perform question answering. Now, at the time, these models weren't widely used. They weren't public for the most part, and they weren't free if they were public. So this meant that the most expensive part of the model training and deployment process was kind of the training phase itself, right? The pre-training and the fine-tuning phase. Because after the model's been deployed, you won't have many users because at the time models weren't really open source or they weren't accessible using APIs and so forth. It's only much later that the model deployment and inference and use phase became significantly more expensive, especially for the more popular model providers. So at the time, researchers were working on trying to make training more efficient, because if we can make training more efficient, then we can significantly reduce the cost of having a machine learning model. So there's only two ways you can make training more efficient. Is either you make pre-training more efficient or you make fine-tuning more efficient. And this paper aims to make fine-tuning more efficient, or fine-tuning more different in some sense. The last thing I want to kind of highlight here before I start talking about the paper is usually this fine-tuning phase contains a small-ish data set that is still massive. It's massive compared to, for instance, the data that a human would see throughout their lifetime, right? But it's significantly smaller than this pre-trained data here. It's slightly cleaner. And it contains a subset of several different types of data. So a lot of these fine-tuning data sets were created and labeled and cleaned by annotators. So companies would pay a lot of money to have annotators create beautiful data sets for them that they can use for fine-tuning. And this meant that there was a lot more control over what kind of fine-tuning data was used. And again, the idea of this fine-tuning data is to clean some of the noise learned during pre-training, as well as to specialize on a domain, as well as to learn some tasks, actually. Because if we're able to control this data so much, then why don't we include some specific tasks? And so these annotators were also paid to create tasks for the model. So these tasks would be things like to extract facts from a paragraph, so knowledge extraction tasks, or they would be sentiment analysis, or they would be classification. So these tasks here were kind of built into this fine-tuning set. So in some sense, instruction fine-tuning and fine-tuning and reasoning and all of these were kind of just built into fine-tuning as one massive training step. And these tasks for the model, researchers noticed that if you have these tasks within your fine-tuning set, that the model is able to perform these tasks and generalize to new tasks during inference, or during test. And so if all you really care about is a model that's able to perform a wide variety of tasks, which is fundamentally all we care about, if the model is able to generalize to a large set of tasks, then we can get the model to do whatever it needs to do, that we want it to do. Then why don't we just take this fine-tuning set, and instead of looking at the entire massive fine-tuning set that we have, let's look at just this task data set within the fine-tuning set. That's the idea behind this paper. The idea behind this paper is, suppose we already have a pre-trained model. So we're not pre-training the model, that's already done. And since GPT-2 is open source, they don't have to worry about the pre-training phase. So instead, let's look at optimizing fine-tuning. And a fine-tuning data set typically contains of cleaner data. It's a large data set that is smaller than the pre-training set, but it's still pretty large. It contains somewhat cleaner data that has a subset of which is created and labeled by annotators. So the way slightly cleaner data might be procured is, for instance, through research papers or through Wikipedia articles, or through very popular open source domains like these, where we know that the data is very high quality, versus this, which would be manually created. Why don't we skip this slightly cleaner data, because presumably it would also be included in this really large data set, and just look at creating tasks for the model during fine-tuning. And let's see whether we're able to generalize to some set of tasks just using a set of fine-tuning data samples where tasks are provided to the model. So that's what this paper does. And if we look at the abstract here, we can see here that they try to introduce a new training framework for few-shot learning, where a pre-trained language model is tuned to do in-context learning on a large set of training tasks. So I want to speak a little bit more about what exactly the paper did and how exactly they went about evaluating the model's performance. So during training, the paper introduces this concept of task demonstrations. So you have a task and you have examples, or they call it demonstrations. Demonstrations of performing the task. And so you have a set of these demonstrations where you have a set of tasks, training tasks, and each of these have some set of demonstrations, and then you train on the task and the demonstration. And this is not pre-training, it's fine-tuning. And then during test, you have a new set of tasks, so maybe I'll use a different color for this. And you have demonstrations again. And this is part of the test set. And it's worth noting that these two sets are disjoint. So tasks from the train set are not part of tasks from the test set. And you pass k of these demonstrations. Demons. That's a bad abbreviation. Demonstrations during inference. So it's kind of like few-shot learning in some sense. And you run inference on this new task, and you see whether the model does any better. So then you test. Now, of course, the big benefit of this is that during training, you significantly reduce the size of this fine-tuning dataset. You don't have a large dataset anymore. You have a very controlled set of tasks and a very controlled set of demonstrations. But the downside is if you want the model to generalize to new tasks, you have to pass in these k demonstrations during inference. So something the authors I don't think really considered was if this model is to be deployed, and I believe they go into the appendix where they mention that it's not really the goal of this paper is not that the model is going to be deployed. It's just research purposes to show that this works. But if this research was to be used in practice ever, and this was a technique that was used, then during inference you would have to pass in k demonstrations if you want your model to generalize well. And what optimal k is kind of researched in the paper as well. I think they come to the conclusion that k equals 16 seems to be a good number. But 16 demonstrations being passed in during inference is a huge inference cost. And it comes with a few problems. First of which, it might be difficult to create 16 demonstrations for your task. The order in which these demonstrations are passed to the model and the format in which these demonstrations are passed is also sensitive. So here I'll kind of talk about this. I'll write it out. So might be hard to create 16 demonstrations. Let's write dems. So this might be one problem. Another problem might be the order of demonstrations matters. As well as the chosen demonstrations themselves. So the chosen demonstrations matter. For instance, one set of demonstrations might not be as good for the actual inference example as another set of demonstrations. So you need a varied set of demonstrations that are still relevant. And don't confuse the model. So coming up with these demonstrations isn't as trivial as it might seem. And yeah, just the inference cost for doing 16, for instance, just shoots up significantly. You might have twice, thrice, 4 times the inference cost per model call. And again, as I mentioned, these days, inference is the most expensive part of creating a model, especially for large companies. So this is a brief overview of how this paper does meta in context learning. So this concept here of fine tuning is a form of in context learning, and that's what ICL stands for. And what the paper tries to do is look at just a small subset and kind of recreate the concept of in context learning, but at a smaller scale, kind of to turn it into a more meta task in some sense. So I just want to quickly skim over the paper and look at some results that they had. Let me see if I have anything else I wanted to talk about beforehand. Yeah. So the other, right, so the last point that I had here is formatting matters as well. And a few things the researchers noted that I'll get into before going to the paper is that MetaICL performs better when you have a large model. So you can't really do this with a small model. It doesn't really work very well. So you need a large model, and this can be expensive. A lot of people don't have access to large model training, so this might not be viable for them. Also, the more demonstration data you have during training and inference, the better. So this is also potentially a problem because at the time the demonstration data was created manually by data annotators because there was no other way of creating this data. It's very particular data for very particular tasks. Certain data sets that exist, for instance, you had natural questions by Google. You might have, a bunch of other question answering data sets, but these were seen as evaluation sets, and of course you don't want to train on your evaluation set. So coming up with a large demonstration set for training is a huge limitation of this method as well. Now, of course, these days you can create synthetic data sets using significantly more powerful models and train small models to do this these tasks. But at the time, we didn't have that. Yeah, so that's kind of an overview of what the paper introduces, and how MetaICL is different from regular ICL or fine-tuning. It's a form of fine-tuning. It's kind of a subset of fine-tuning, if you will, that aims to generalize a model to perform tasks that it hasn't seen before in using a fine-tuning method that is proposed to be less expensive than regular in-context learning or existing fine-tuning techniques. It seems as though my pen has died, so I'll charge this. So if we just go into the paper, the other method of in-context learning that the paper mentions, apart from just fine-tuning, is kind of few shot learning, just passing a set of samples into the model during inference in order to give the model some more context as to what it's trying to perform. So that's another form of in-context learning that the paper mentions that was done in research at the time. And so their idea is to combine that form of in-context learning where you do few-shot learning with demonstrations at test time with the idea of fine-tuning. So yep, so here you have meta training. So during meta training, you have some set of training tasks, and then you have a set of training samples. So these training examples are essentially your task demonstrations, and something that's important here is this over here. Ni is significantly larger than k. So during inference, you pick k tasks. So during inference, you have k tasks or k demonstrations passed. But your total set of demonstrations during training is significantly larger. If during inference you had to pass in the same number of demonstrations that you saw during training, then it's kind of pointless to perform this kind of training. You're just passing your entire training data into the model. And if you aren't able to create smaller demonstrations during inference and generalize to smaller demonstrations during inference, then you're going to have to consistently create huge demonstration data sets for each task, which is not feasible. So this here is quite important, that the number of training demonstrations for a task is less than the number of inference demonstrations. So this here would be one pair. This is one pair. So input and demonstration. So task and output, or task and result. So we have exactly ni of these for each task ti. So we might have tasks T1, let's say TD, or TC actually, C meta training tasks. And then each of these has a set of examples, X1, Y1, X and 1, Y and 1. And so this is kind of how our data set is structured during training. What else do we have? During inference, we use an unseen target task. So this task is not from our training or meta training task set. And then we use k examples during inference. And then we pass in these k examples to the model. So this is the k demonstrations being passed into the model. And this is our new sample that we want to compute the answer for. And we want to maximize the probability of this solution. So we want the model output to be the class that we're looking for. So here, I think they focus on classification tasks mostly. So this is the class that the model outputs. So we look at the distribution of classes, class probabilities. So maybe class 1 has some probability like this, class 2 has some lower probability, class 3 has 0 probability, class 4 has maybe slightly higher probability. And then we just take the maximum out of these, and that is considered the model output. So that's the inference technique that they use. Inference and I guess inference sampling technique that they use. Also, last thing, during training, K+1 examples are chosen from this larger sample set, and then the training is done on these examples, as well as the new tasks. Sorry, these examples here. So these are the training examples, and then this is the new task that they train on. So during training, the model receives these demonstrations as well. So it learns to learn, in some sense, from the demonstrations that it's seeing to generalize to the K+1 instance of this task. And I think the idea behind this is quite neat. The idea is that if the model learns to take these K demonstrations and generalize it to this K+1 demonstration, it's no longer learning this particular task, but it's learning to learn a particular task, right? So if I showed you a new task, or suppose I release a new video game and I show you a few examples of how to play the video game. The idea is not that I can now play this video game, but the idea is now I can look at any few examples of any video game and learn how to play it. So it's kind of a learning to learn kind of paradigm. And this is one of the first papers that introduced kind of learning to learn. And it becomes a lot more important when you look at ideas like test time training that have popped up more recently. Test time adaptation and memorization. So I'm not going to get too into the results that they saw, but I will go into some of the more interesting ones, in my opinion. Here, this is their main results, and they train using GPT-2 large for these results. I think the two main models they used were GPT-2 large and GPT-J. These results are slightly misleading. For instance, this here is bolded to be the best figure in the table. However, the best figure is actually this one here. So it's slightly misleading as to what they've bolded. Really, the ones that, or the technique that does best mostly across the board, is just regular fine-tuning, including the meta-training data. The paper also uses two different inference techniques. They use MetaICL and channel MetaICL. I wouldn't go into the difference between those two. You can have a look at it in the paper. But here, let me see where they introduce it. Channel MetaICL. So they basically do a reparameterization of their objective in some sense. And then they flip what information is passed into the model. So it's something along the lines of instead of passing in, this, or trying to get this objective from the model where you have this the structure of you pass in these K demonstrations, and then this is your class output, and this is your test sample or train sample or whatever. You repeat this over all of the possible classes for your task, and then you look at the maximized class output. So it's slightly different. I don't think it matters too much. But yeah, so I think it's slightly misleading that they embolden these results, although fine-tuning along with meta training did better in almost all aspects. Same thing here with these unseen domain results. You just have better results with fine-tuning and meta training. I guess this one, meta training did better, and then it's kind of a mixed bag of results. Here, the paper looks at how many samples are needed. So this here is K on the x-axis. And clearly there's an upward increase, an upward trend. The more samples you give it as demonstrations during inference time, the model just performs better. So we can see, though, that results kind of plateau after k equals 16, which is why I said k equals 16 seems to be a good value for how many samples to pass into the model. But yeah, the number of training tasks as well, so this here is C, the number of training tasks, also seems to improve model performance slightly across all models and techniques. And yeah, that's pretty much what the paper does. I think it's a pretty influential paper, and the idea here was quite significant in the learning to learn regard. So this was a big idea that was introduced of learning to learn. And another idea that was introduced is that we can create a very small fine-tuning set, call this, MetaICL or whatever, and train on specific demonstrations, and that eventually kind of, became IFT, although it didn't directly inspire IFT. IFT came out around the same time with GPT-3, but it was thinking along the same lines as IFT, and I think the idea behind this paper is quite neat. So yeah, I will put a link to this where I can, and hopefully there isn't anything significant that I missed out. The appendix goes into varying the size of the language model, showing you that large models just do tasks better. They go into studies of what tasks were helpful and what tasks were unhelpful during training. And yep, they give a small mention as to the fact that there are potential risks, and that this paper is considered to be a research prototype rather than a deployable system. That makes sense. But yeah.